coming in. I'll wait for anyone to come in. I don't want to talk to myself. So I'll wait for you guys to come into the chat in the meantime. So I won't start right away until more people come in. Don't be shy. Anyone's here? Okay, all right. Okay, I'll wait a bit longer, see if anyone comes in. If not, I'll start anyways. Okay, I see we have one person. All right, I'll get started. So welcome. If you don't already know me, my name's Jason, and welcome back to S.T.E.M Online Academy, where we discuss math, physics, and technology wielded together to help create and strengthen your mathematical intuition. Okay, so last time, for those of you who've watched my videos, we were discussing an interesting topic, something to do with Fourier transforms. Okay, Fourier transforms, Gaussian integration, and the applications of those integrals. Okay, as long as you have a strong background in integral calculus and in your algebra, you'll be fine with this. Even if you haven't seen this type of stuff before, like the applications or any of that, you'll be fine as long as you know how an integral works. I used to be fluent at this. All right. Okay. So, as I said, last time we were looking at talking about specifically Fourier transforms and stuff like that. Okay. Now, today is going to be office hours. So, what that means is we're going to be looking at what we did throughout this week. Okay. In the last last two live sessions. Okay, so any questions that you have relevant to Fourier transforms and Gaussian integration and their applications as well. Okay, so pretty much any of the stuff that we discuss has to be relevant, though. Okay, so relevant to the fields that we've discussed. You can ask me questions, any questions on those areas of math, of applied mathematics. Okay. And by the way, this is, for those you don't know, this stuff is from my book, Advanced Integration Techniques, where we look at mathematical methods and the applications of these integral methods. Okay. All right. So let's get started. I was going to look at talking about some interesting stuff here. So let's get to the. I'm going to share my screen. Okay, so let's share the screen. Entire screen. I will start sharing. Okay, let's go to the whiteboard. Okay, let's give me a moment here. All right. So yeah, so here it is. We're going to be talking about Fourier transforms, Gaussians, and the structure of waves. How these pretty much how these integrals have applications in quantum mechanics. Okay, I'm not an expert in quantum mechanics, so in terms of that, you probably want to ask someone else. But I know the mathematical applications, some of the mathematical applications in quantum mechanics, and they're included in my book actually. Okay, so integrals can be applied in quantum mechanics, which is really cool actually for those of you who are interested. Okay, so as I said, today's menu, you can say, is mainly to take up some homework. Last live show, I gave a challenge question on Fourier transforms. For those of you who've looked at or watched the last live show, we were discussing some of the challenge problems. I gave you like one or two challenge problems. So any of the people who also saw the last live show or who are in this live show, you'll probably will probably be relevant. For those of you who are new, I'm going to see what happens. I might just skip over the homework and I'll wait for other people to come in and then we'll take it from there. All right. Number two. So yeah, make sure you ask me any questions you have on the relevant chapter, right? Number two, we're going to look at maybe a Fourier transform warm-up. The reason why I say that is at the beginning of any lesson, it's easy to, to not have your head in the game. I feel like this will get you focused and sort of remember what happened last time, exactly what we did, okay, in case you forgot. So this will sort of put you in the mood to start doing Fourier transforms. Part three, we'll look at a residue and Fourier fusion. I'm going to discuss what a residue is. Okay, residue calculus is interesting. Cool. Okay, it's just elementary complex analysis. It's elementary complex analysis, not rigorous complex analysis. That's just that would be brutal. Okay, so my book includes some elementary residue calculus, but not the very rigorous form. Okay, that's just that'll be a bit too crazy. All right, and then number 4, we're going to look at bringing all this stuff alive. So what I mean by that is we're going to look at a visual simulation on waves, and wave functions, pretty much. Okay, so I think that'll be interesting to sort of, so that's why you guys can see what's going on. All right. Okay, so let's get back to the whiteboard. So since I don't see anyone that I can remember from last time, I'm going to leave taking up that homework question for later. If anyone shows up that was from the last live session, or who just wants to tackle, let me know. This is the homework question from last time. Okay. So it's to show that the Fourier transform of the function f of x is equal to e to the negative a power times absolute value of x is the following Fourier transform to a all divided by a squared plus omega squared. So we want to prove this. Let me highlight. We want to prove that we get this Fourier transform. Okay, so it implies I need to put an implication, because implication would mean that this is what I'm trying to prove. Okay. If there's anyone in the live chat, anyone who knows what a Fourier transform is or doesn't know, I can put it up right now. Anyone at all? Don't be shy. You can come in. This channel is for anyone who has, as I said, a fluency in calculus and linear algebra. Okay. All right. So we're going to be looking at this guy right here, the Fourier transform. This is what we want to prove. And let me just remind you what a Fourier transform is. I think the smartest thing is to go back to the theory. So that's what you remember what the theory is. If you don't know what it is, but as long as you know integrals, it will come automatically. Okay, so nothing that complicated, at least yet. Okay, so let me just highlight this. Okay, so we'll just put it over here. Okay, I'm going to say DEFN for definition. Definition of what a Fourier transform is. Okay, so a Fourier transform. Okay, right. So let me put over here. Let f of x. Just 1 second. So I'm just going to put a definition here. So let f of x be a function. I'll say f of t. Usually we use t space. So let f of t be a function of t. Be a function of t. Okay. And let capital curly f. Okay. So let capital curly f, okay, of f of x, capital curly f of x, in parentheses, as a function of omega, okay, be a Fourier transform, be a Fourier transform, okay, be a Fourier transform, okay. All right. Anyone have questions? Let me know. Nothing yet. Okay. All right. So curly f, capital curly f of f of x as a function of omega be a Fourier transform. F of t is a function of t. Okay. Where a Fourier transform, where a Fourier transform converts converts going from T space, okay? So going from T space, so Fourier transform converts going from T space, okay? Right, so you go from T space, right? So converts from going from T space to omega space, okay? So omega space, okay? And the way we convert from T space to omega space, anyone have ideas? Oh, hi, yes. Hi. Have you, what's the last? You've been in my live show before. I think we have someone here before. I think I've seen you before. Can't remember. Alan, Anton, Andrew. Have you been on the live show before? Can't remember. There's quite a few people. There's too many people who can't remember everybody. Let me know if you've been in the live show. Let me know, Alan. I'm assuming you've been in a live show. You have a background in mathematics. All right, so we're looking at, don't worry if you're shy, I'll continue on. I assume you're interested in this stuff. So we're going from the Fourier transform, right? Fourier transform converts from going from T space to omega space, okay? So what does that mean exactly? That means I'm going from some, let's say, for instance, on the side here, I'm going to draw a graph, right? Let's say this is a function of T. Let's say this graph here is a function of omega, okay? Let's say one graph is like this. Doesn't matter. All right. Maybe another graph, and then the omega space comes out to be something like this. Okay. This won't be accurate, but I hope you get the point. Right? One's a function f of t. The other one is a capital F, capital curly F of f of t, which is going to omega, transferring from t space to omega space. Okay. So capital f of t as a function of omega. Okay, so one function of t from t space goes to a function of omega in omega space. Okay, all right. And the way we measure that, do you know how to calculate this? I'm not understanding. 277,515. Confused. What do you mean? Start to speak English because I'm not quite understanding. What do you mean? English. Do you speak English? Start to English. Be handy if you speak English. Anyways, I'll continue on. All right, so we've got over here, right? So we have a Fourier transform, capital curly F, f of t. And the way we measure from going from t space to omega space is using the following formula, right? Is that, let me put over here, right? The Fourier, right? Capital curly F of f as a function of t as a function of omega is equal to the improper integral from minus infinity to infinity. Okay, be careful there. of f as a function of t times e to the negative I omega. This is a general Fourier transform from a negative I omega t dt. Have you seen this before? Anything? Okay. Just to bring it back for any of you who have, seen the Fourier transform, or if you forgot it, or first time, that's what it is. As I said, this is mainly an office hour type of live session. So any questions that you have on the homework from the last live session, right? As I said, I gave out this problem right here. Okay, so this one I'm highlighting. This, you want to prove that when we have a function f of x from x space e, which is equal to e to the negative a power of absolute value of x, implies that we get a Fourier transform of f of x as a function of omega is equal to 2a all over a squared plus omega squared. Okay. So for anyone who has seen my last live show, right? If you've seen my last live show, I left the homework problem. We're going to discuss it. Okay. So that's what's going to be relevant. If you have not seen the last live show, that's okay. Ask me any questions on Fourier transforms, and Gaussian integrals, and how they apply to waves, algebraically, and also graphically. I can be able to help them. Yeah, I need to wait. Probably gonna have to wait for some people to come in, because right now we only have like 2. Unless you guys have a specific question at the moment. No, you got a specific question. Okay, I'm seeing some English now, Alan, but I don't understand meaning in my life. I add. What do you mean, Alan? Okay, what's that for, pun for real? Please, it needs to be relevant to our live session. I think I'm understanding. Not understanding quite. Nope. What do you mean? X and Y. Y. Ah. You mean the Schrodinger? You talking about Schrodinger cat? So yes, you agree, right? I mean, sure, yes. Yeah, this has applications to quantum mechanics. So yes, unless we're talking about the time dependent or time independent Schrodinger equations, that's what I know. But I know that yeah, there are solutions for that that requires integration, especially for your transfers. Let me diverge here. It may not be exact. It's not a Schrodinger equation, but I'm going to show you that since you're interested in cats and boxes, where a Fourier transform can be applied to. 2, 3, 4. What does that mean? Anyways, I'm going to show you something in a moment. I just want to see if there's some other people coming in. I don't know. What do you mean by that? Yeah, I'll be waiting for anyone else to come into the live chat. Again, this is a STEM Online Academy, right? Where we discuss, where we use mathematics, physics, and technology to help strengthen your mathematical intuition. Okay. Right. So just letting you know, welcome back to STEM Online, right? Where calculus, physics, and technology collide to build true mathematical intuition. Right. Tonight's special is a special session. Right. It's the office hours. I'm just repeating myself. I said this a few times, just in case for anyone who jumps into the live chat who hasn't already heard what I said before. I'm just making sure that everyone understands that they're in the right place or interested in the right place or whatever. Okay, so it's as I said, a special day today. We're just discussing any it's office hours. So any problems, questions you have on from the last live session, you didn't have to be in part of the last live session. Okay, but as long as it has to do with Fourier transforms, a Gaussian integrals, and etc. Okay. All right. Anyone else? Okay. All right. Okay. So I think I'll just get started. Okay. So we're going to be looking at, since it's office hours, I'm just going to put some interesting stuff up. Okay. In case anyone wants to look at something interesting, this may attract people to see how Fourier transforms, wave functions, everything works. Okay, so let's say, for instance, okay, let me go to Desmos here. Hopefully you can see it. Okay, just one sec. Just give me a moment. Yeah, let me get out of that. Let me go to Desmos. Okay, should be able to see Desmos. All right, so in Desmos, oh, 1 second here. Let's share my screen. me see, stop sharing. Just 1 sec, stop sharing. Let's go to share screen. Okay, let's go to specifically. Yeah, insert. Yeah, share screen. Okay, window. Nope. 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 Let me do that. You should see. Yeah, you should see the white. Yeah, you should be able to see it. Okay, so looking at the Desmos graph. Okay, I've put up an interesting function that we're going to be looking at. Okay, so actually I won't do this. I might do e to the negative x squared, actually. Let's keep it as simple as possible. Okay, for this demonstration. Alrighty, negative x squared. Get rid of that, get rid of that. Okay, I might also add a slider as well. 1 second. Yeah, the expression. So y equals ae to the negative x squared, negative x squared. Okay, we're going to add an a value, so a slider on that. Yeah, I think that'll be interesting. Okay, as you can see, I'm going to put a equals negative x squared, maybe k, also a k value. Add a slider to k as well. And I need to put some restrictions. So as you can see on Desmos, you can make graphs, right? So I'm going to make graphs of a typical bell curve function y equals e to the negative x squared. The reason why is because it's relevant to the Gaussian integral, right? If I integrate a bell curve, I'm just getting a Gaussian integral, right? So we're going to look specifically at this, okay? All right, so we're going to look at specifically at this function. So what I'm going to do is so A and K are parameters. A is a vertical stretch on E. Obviously, K is some sort of horizontal stretch or compression on the function. Okay. All right, so I'm going to put K being, yes, that slider. I'm going to let K equal, K be negative 1 to 1. Let's see how it behaves. Nope. Bad. Let's see, 1 to 2 or something. Okay, let me see, maybe negative 1 or 0. Put it at 0, so 0. I'm going to put at 1 and 2. So 1 and 2. For the A vertical stretch or compression value, I'm going to put constraints on A. Okay, so there's going to be some constraints on A. All right, so the constraints on A. Okay, let me put the constraints. I'm going to say negative 1 to 1. Actually, yeah, negative 1 to 1. Let's see what happens. Okay, being, but I have to zoom in more. You can see this. Okay, so you can see what's happening here with this graph, right? Okay, as I vary A and K. So when you do a Desmos graph, you always want to make sure that you define your function, then you have to define the formula of the function that you're dealing with. So you have to put some parameters. For instance, in this case, I put A and K. A is the vertical stretch or compression. K is the horizontal stretch or compression of the function of the bell curve. Now, the point of doing this is I want to show you, given parameters A and K and varying A and K, right? You can see the behavior of how it's operating. All right. Anyone interested in this? Can anyone tell me what type of translations are happening? Even though I already gave a hint. Anyone know what type of translations are happening with the graphical simulation here? So I have a graph, and you can see that I have some constraints on K and A. So K I made vary between 1 and 2 included. Okay. So pay attention to the blue curve. Okay. At the same time, I may also vary the red curve as well, putting a equal to negative kx squared as well. And see if there's anything that happens. Actually, this is better because when I do it like this, I only want to show you what's happening with one curve. You don't need two curves. So you have one bell curve here and you can see what's happening. Okay. So this is obviously a bell curve, right? So a bell curve is applied in probability and statistics. Okay, it helps us calculate, well, not just calculate, but yeah, calculate means, standard deviations, and stuff like that, right? Means, standard deviations, all sorts of interesting things. Okay, I just wanted to show you this, but more importantly, it helps us calculate something very interesting, root pi, right? Okay, the area under a Gaussian under a bell curve is a Gaussian integral. Okay, right. So you can see here we're just dealing with that. We're just showing that we're having a bell curve oscillating up and down, stretch with the vertical stretch of a factor of a, k being a horizontal stretch of compression. Okay. Does anybody know what is going on with the curve here? What's going on with the curve? Yes, I put A and K. Does anyone know what A stands for? And not only what it stands for, how it correlates to the graph, like why my curve is going up and down. Anybody know? Just waiting for some more people to come in before I start jumping into stuff. I always try to figure out if I should just jump in and start doing the problems and nobody's here, or even if you have one or two people, I feel like it's not enough. You have to wait for other people to come in, or just wait. So that's why people aren't getting lost and saying, "What the hell's going on?" But I think I'm gonna personally wait. In the meantime, I put something interesting up. All right. All right. So since we're talking about Fourier transforms, okay, I think we're going to look at a specific Fourier transform. All right. If you look, because since this is supposed to be office hours, okay, I'm expecting you guys to have, a foundation in a strong foundation in calculus and linear algebra, right? As well as maybe a little bit of physics, but you don't really need to know it as long as you know the math. The application is straightforward. But yes, all of that, and also if you have any understanding of Fourier transforms in your undergraduate or graduate classes, you can ask me. Okay. And since we're discussing Fourier transforms, it is office hours, and anything has to do with Fourier transforms. I'm going to put something interesting up here. So let me just stop sharing this for a second. Just give me a sec. Okay, I'm going to stop with. Yeah, we go back here. Stop the sharing. Yes, sharing. And then I'm going to go all the way over here. Share screen. Entire screen. Okay. And we're going to go back to the whiteboard. Okay. So I'm going to leave that up for later. Okay. What we're going to be looking at right now, in particular, maybe I should go to another page here. I won't talk about that yet, unless someone's coming in. Let's go to a new page. Pages. Okay. We're going to be looking at a quantum Fourier transform, all right? So last time I talked about deriving a special type of Fourier transform, okay? All right, so let's talk about it. So in the meantime, I'm going to talk about interesting stuff with Fourier transforms, and anyone who wants to come to office hours will ask me relevant stuff on Fourier transforms. Okay, so Fourier, let's go to Fourier. So Fourier transforms in QM, so in quantum mechanics, applied to quantum mechanics. Okay. I think that's what we're going to be discussing. Right, so every quantum state is a superposition of frequencies. That's what it is. Okay, and Fourier transforms helps to measure that. Okay, so think of that. There's a reason why I put that visual diagram above earlier. Okay, from Desmos, right, was to show you guys that that's usually how what we're dealing with is wave pulses or wave functions of some sort, like e to the negative x squared or any other type of function, right? Because quantum states is pretty much superposition of frequencies, right? And Fourier transforms is pretty much, you can think of the language between position space and momentum space. Okay, let me explain. Okay, last time we talked about the following. Okay, we said that psi of p, okay, so 1 second. So we derived that psi of p was equal to 1 all over the square root of 2 pi, and then it was integral from minus infinity to infinity, okay, of psi of x, right? So psi x times e to the negative ipx dx, where p is the momentum. P is momentum space. Okay. Well, I should just say p is the momentum. Okay. So, all right. And we're going to do something simple here. We're going to use something like this. So this is a Fourier transform, right, in quantum mechanics. This is the Fourier transform of momentum space. Okay, so let me explain. So this is, I'm going to highlight this. This is a Fourier transform in momentum space. Transform in momentum space. Momentum space. Let me see if anyone is coming in. Not quite, at least not yet. Anyways, in momentum space. Okay, so in momentum space. Now this Fourier transform. Okay, so this Fourier transform right here. We're going to use the function. So let's say, and psi of x, you know psi of x. Psi of x is the wave function. Okay, so psi of x here is called the wave function that I highlighted. E to the negative ipx is power is the plane wave function. Okay, so for nomenclature, right? Psi of x is the wave function. E to the ipx is the plane wave. Okay, and I'm going to say this, right? So let's say example problem. So let's do an example. Okay, so an example. So example problem will be, let's say psi of x equals e to the negative x squared. So that function that I was plotting on Desmos and showed how it moved as a wave pulse, that's why I did that simulation, so that it can be a wave function, right? Doesn't matter what I call it. Usually we use psi of x for wave function. Okay, we're going to calculate its it's a wave function as a function of momentum. Okay. All right. So that's what we're going to be doing. So anyone want to try this? Anyone at all? It's really fun stuff. Don't be shy. I know there's guys out there who are interested in math and physics. Okay, so we're going to be looking at solving the following. Okay, so this guy right here, psi of x. Okay, so let's just say this is maybe a problem. So problem. Trying to solve this guy right here. Okay. I'm going to solve this. So solve this. So the question is, I just write it as a formal question. Okay. Find, I'll just say find the QFT quantum Fourier transform of the function f of x, where f of x, not a function, wave function, to be more scientifically precise. Psi of x is equal to e to the negative x squared. I don't want to really start anything unless someone's coming in. Anyone? Again, this is office hours, S.T.E.M Online office hours. So welcome back to S.T.E.M Online Academy. We are where we help people with math, physics, and technology increase their mathematical intuition. Okay. Today is a special night. We're looking at its office hours, so we're just going to be going through problems on Fourier transforms and Gaussian integration and their applications. Okay, so if you've either seen my last live show, even if you didn't, but you know about Fourier transforms, and you need help with Fourier transforms, you're conceptually stuck with Fourier transforms, anything like that, this is the place to ask. Okay. Any type of help, I can help you with Fourier transforms, Gaussian integrals, at least make it relevant from this week's live shows. Okay, let's go to the whiteboard. Okay, so stuff like this. Okay, we're going to be looking at different types of stuff here. Last time, as I mentioned, right? Not only is it office hours, but we're also going to retake and relook at some questions that I talked about from last class. I thought it would make the most sense to look at the homework question that I assigned. Okay, even if you weren't in the last live session, but you're interested in challenging your Fourier transform wit, there is a problem right here that I've put on the board. Okay. So for f of x is equal to e to the negative a absolute value of x power, and we want to prove that the Fourier transform is highlighted in red. Interest on Fourier transforms. Come on, guys. right? So just looking at this. And to make sure you guys remember what a Fourier transform is, I'll read the definition again. So let f of t be a function of t. Let capital curly f as a function of f of x, as a function of omega, be a Fourier transform, where a Fourier transform converts going from t space to omega space. Okay. All right. So what does that mean? It makes the most sense for me to ask the questions, both not just the problems. I also want to make sure you guys, the most important thing about this channel, as I mentioned, is to help with your conceptualization of advanced mathematics, okay? And the way to do that is not only just the problems, but also asking conceptual questions right off the bat, right in the moment, and also paying a huge amount of time to the methods and theories behind advanced integration, which is what my book is on, okay? All right, so let's go over here. So advanced integration techniques, okay? Both the theory, or you can say one or the other, as long as you know the theory or the specific mathematical method, you need to know it before tackling the problems. Otherwise, these problems aren't going to make that much sense, okay? Right, so looking at making sure you understand the theory. So first off, a Fourier transform, right? Right, it's an integral, it's an improper integral that I've highlighted below. Okay, below in red, blue, sorry, the very bottom equation. Capital F of f as a function of f of t as a function of omega is equal to the integral from minus infinity to infinity of f of t times e to the negative I omega t dt. So that's a regular Fourier transform. Now, I just want to make sure that we are consistent with our last live session. So that's why I'm going to be very, very, very strict in terms of what will be asked, right? It needs to be relevant to what we discussed in the last live shows, okay? All right, so we just... Okay, and this time we have a Fourier, and also not just that, just reminding you, last time at the end of the class, it was mainly a mathematics class. That's what my book is on. Right? But also included some applications of Fourier transforms in quantum mechanics, right? And I talked about, at least from the last live session, for those of you who are interested in QM, okay, you got quite a few people probing me more specific things, Fourier series and Fourier transforms, right? Again, both Fourier series and Fourier transforms, there's three main applications: signal processing, okay, that's very handy for signal processing of piece or any type of signal. Musical instruments, okay. So Fourier series and Fourier transforms are very, 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 very important when it comes to musical instruments. How does anyone know how Fourier transforms are applied to musical instruments? Anybody at all? Anyone have an idea of how Fourier transforms? Just going on to the history of Fourier transforms, and not just the history, but the applications. They can be used to create scales, musical scales. Yeah, very interesting stuff. There's actually a whole topic about that. It's practically a mathematical science. Okay? There's something called Fourier analysis. Okay, this book goes into it a little bit. Okay, I don't go into Fourier analysis per se, but I go into a little bit into Fourier analysis, at least in terms of Fourier transforms, Fourier series. But there's no you don't have to worry. There's no epsilon epsilon delta techniques at all. Okay, those always scare people. That's what I'm saying. It helps again. S.T.E.M Online Academy, where we help with advanced mathematics and physics, right? And our techniques are pretty much trying to help you guys strengthen, really strengthen, number one, critical thinking, two, visual spatial skills. That's why I like using modeling diagrams. And three, from this, the third one, which will come from step 1 and step 2, is increasing your mathematical intuition / maturity. Okay. And that's why I have this book. All right. So yeah, that's what this book is all about. Really building up. As long as you have a foundation in integral calculus, as long as in calculus and linear algebra, and you want to learn more on integration and its applications, then this is the place to be. Okay. And if you're interested in the book, you can purchase it in the link. I'll talk about that later. Okay, anyone in here? So we're talking about Fourier transforms. Okay. All right. So since no one's coming in, I'm just going to go through some problem. Okay, it's maybe a basic problem. Let me see which one is easier. This one or the one the last time that I should be taking up. Yeah, I'm going to talk about that. Yeah. Yeah, I might talk about that. So we're going to talk about the solution for f of x equals e to the negative ax. Okay, let's do the solution. All right, so let's talk about the solution for the problem, right? We want to show that the Fourier transform of the function e to the negative ax gives us that Fourier transform in red. Okay, so here's the proof. Okay, I'm going to try doing the proof anyways right now on the spot. So proof. Okay, so here's the proof. Just 1 second. Proof. Okay, the first thing. How am I going to show that capital F is equal to 2a all over a squared plus omega squared? Well, since we know that, so I'm just going to say because f of x, okay, so because f of x is equal to e to the negative a absolute value of x power. Okay, we're going to substitute. Okay, so we're going to substitute. You see substitute. I'm going to substitute into our formula, the regular Fourier transform. Okay, and that states that if you have capital curly F as a function of little f as a function of x as a function of omega, here x is our t space, is equal to the integral from minus infinity to infinity of e to the negative e to the, let me see here, let me not put that in yet, integral, improper integral of f of x, okay, so f of x times e to the negative I omega x dx. That's the first step. Anyone know how to integrate this? That's how we're going to integrate this. Very straightforward, right? So the f of little f as a function of x as a function of omega, right? Right. So I just put here. I'm going to use a different color. Blue sometimes is overwhelming. Let's do that. Let's use green. Okay, so we're going to use integral from minus infinity to infinity. F of x was e to the negative x squared, so e to the negative x squared times e to the negative I omega x dx. Okay. I think there's any confusion on that. Any confusion? Any confusion on the Fourier transform? Again, this is a special night. This is office hours with S.T.E.M Online Academy. Again, for advanced mathematics and physics, where we build strong mathematical intuition by looking at problems that require using a visual spatial, strengthening some visual spatial awareness and increased critical thinking. Okay, so we're going to look at, again, this is from the last live. So the last live show was on Fourier transforms and Gaussian integrations. So my office hours is mainly for you guys to ask me questions that you had, anything you had trouble on. Okay, anything you had trouble on that was relevant to this week, right? Fourier transforms, Gaussian integrals. Okay, and we're also, it's not only just not just office hours, but also I can talk about interesting problems that I put on the board that will be relevant to this topic. Okay, on Fourier transforms and Gaussian integrals. Okay. Right, so we have a Fourier transform here. Okay, so I'm just going to go through this. I thought it would be handy doing a problem like this because I assigned it last week, not last week, last live session. Okay, and asked if anyone did it, anyone solved it at all. Still waiting for those people to come back. If not, and it's your first time seeing it, and you know a little bit about Fourier transforms, go ahead and get started on the problem. Function of omega. Now, what ends up happening here, okay, something interesting happens. We can rewrite this. Okay, so this is the integral from minus infinity to infinity. These both have similar bases, right? Doing a Fourier transform is easy. There's nothing complicated about it, right? What happens when you have similar bases and you're multiplying them? What happens with their powers? It's very basic. What happens? You add the powers, right? So now it's written as the integral from minus infinity to infinity of e to the power of negative. I can factor out the negative x squared plus I omega x, right? Dx. Okay, so we have this. All right. Now, I don't want to fill in the spaces here because I feel like, especially if you either have a background in Fourier transforms or you've seen my last live show, you should have learned how to take a Fourier transform easily. So by that reasoning, I'm expecting you to learn something and you should know how to do this. Okay. Anyone know how to solve this integral the way it's written below in yellow? Anybody at all? How do we solve this improper integral where e is raised to negative of x squared plus I omega x? Notice what's in the exponent. No, it's a standard quadratic equation, right? It's just a standard quadratic equation. What I mean by that is that we just have this. Look here. It's a standard quadratic equation written in standard form, right? What do I mean by standard form? This is written in the form ax squared, right? So ax squared. Sometimes these pens, silly, plus bx plus c. I'm going to make my writing better. My apologies. Plus bx plus c. Okay, so we're in standard form. The exponent's written in standard form. All right. So knowing that, how can we compress this to make it simpler to understand? Well, there's one way to do it. We complete the square. What does completing the square mean? Complete the square, right? We need to translate from ax squared plus bx plus c to a plus b all squared. That's what it means, right? So obviously you guys understand what completing the square is. So I'm going to complete the square. It's right here, completing meaning the square on the exponent. Okay, so what I'm going to do is take b over 2 all squared, right? So b over 2 all squared. So I'm going to do b over 2 all squared. Okay, and then b in this case is I omega, right? So all brackets I omega, because that's the constant. B is a constant, I omega is a constant independent of x, divided by 2 all squared. Okay, and this would expand out to I squared omega squared divided by 4, which is equal to negative omega squared divided by 4. Okay. Any questions on that? That's to be straightforward. Right, so negative omega squared divided by 4. Okay. Now we're going to input that information in. Okay. Oh, wait a minute. I just realized something silly. Before doing that, I probably should split up this integral. Yeah, we have a problem. Yeah. I just noticed something. I made a stupid mistake. I used e to the negative x squared. I'm supposed to use e to the negative a, absolute value of x. So sorry about that. Damn it. My apologies. Yep, because we're trying to prove that if we have a function e all to the power of negative a times absolute value of x gives us a Fourier transform of what I wrote in red over here, 2a over a squared plus omega squared. Okay, so yeah, careful of that. Okay, so get rid of this and this. Okay, so what was our f of x? F of x was equal to e to the a absolute value of x. Okay, so it's going to be integral. Let's write this again, minus infinity to infinity. I had my wrong f of x. Also thinking from another question that we were going to discuss, and also we discussed last class, which was relevant. Okay, so f of x was equal to e to the negative a absolute value of x times e to the negative I omega x dx. Okay, and then from here, this is equal to the Fourier transform is equal to the integral from minus infinity to infinity of e to the negative. Now, careful. We have the absolute value of x. Okay, right? So we have to deal with that as well. So first off, I'm going to use this almost the same thing. Factor out a negative. Have a times absolute value of x plus I omega x. Okay, dx. Any questions so far? Any disagreements? Disagreements. Again, this is office hours for S.T.E.M Online Academy. Okay, so we have this right now. So we have e to the negative whole power of a times absolute value of x plus I omega x. Okay. Then from over here, what we're going to do is we're going to rewrite this. Not yet, actually. There's two cases that we need to look at because we have the absolute value of x. So note, I'm going to write over here, note. So this is very important, capital note. that the absolute value of x, what it's equal to, so the absolute value of x, absolute value of x is a piecewise function where we have x if x is greater than 0, if x is strictly greater than 0, greater or equal to 0, and negative x if x is strictly less than 0. Okay, so just remember that's for a piecewise function. So we have case 1 and case 2 for this guy over here. Okay. So the way to deal with that is going back here. So we had, remember what we had here, we had a Fourier transform, okay? Fourier transform that we were trying to prove. Okay, so Fourier f of x as a function of omega, okay, is equal to integral minus infinity to infinity of e to the whole power of negative a absolute value of x plus I omega x dx. Okay. Now we're going to have case 1 and case 2. Let me highlight. So case 1, when absolute value of x has to equal to x. Absolute value of x is equal to x. Okay. Because it either equals x when it's absolute value of x, or negative x is equal to absolute value of x. There's two cases. So we have to do each case individually. So doing the Fourier transform, okay, Fourier of f as a function of x as a function of omega is equal to the integral from minus infinity to infinity of e to the negative power, all in parentheses, ax. See how I got rid of the absolute values? Because I'm taking absolute value of x equal to x plus I omega x dx. Again, this is office hours. So like anyone who's just coming into the chat to clarify what's going on here, because if I don't, you'll be confused. You'll be like, what? This is S.T.E.M Online Academy. We're looking at office hours, anything on Fourier transforms or Gaussian integrals, okay? Whether you see my last live show or not, but you have the understanding of integral calculus, we're going to be discussing conceptualizations you want to learn, or that you've had difficulty with. If you've had any conceptualizations that you've had difficulty with Fourier transforms and Gaussian integrals that you need cleared up, this is the right place to be. Okay, so we're going to go back here. And we're also going to be looking at a problem that I assigned last class. It was verifying, I'm going slowly through it because I want more people to come in, verifying that in red that the Fourier transform of f of x is equal to 2a divided by a squared plus omega squared. Okay. All right, so we have this Fourier transform right now. Okay. Now, the way to do it, as I mentioned before, okay, is we're going to use, we're going to use some type of completing the square here. Okay. Actually, it won't be needed to use the complete square. Nope, no complete square because there's no x squared here. Okay, so we're dealing with this guy right here. So we need to be able to integrate. How can we integrate this? I know it looks intimidating, but before doing anything, I can rewrite this Fourier transform, which is a function of omega, which is equal to the integral from minus infinity to infinity of e, right? E to the negative parentheses a plus I omega, a plus I omega power parentheses x. The x can come out. It's a common factor with respect to x. Okay. Anyone interested in Fourier transforms, please. Fourier transforms. Just waiting for some more people to come in so I can continue. At the same time, anyone know how to integrate this? we're looking at a problem from last live show. If you haven't seen the last live show, I assigned a homework problem. We show that the Fourier transform of the function f of x equals e to the negative a power times the absolute value of x is equal to the Fourier transform in red. Just waiting for some other people to come in. Type Fourier in the chat if you've used Fourier transforms before. Anyone type Fourier in the chat if you've used Fourier transforms before, or if you've, maybe haven't used them but seen them before, type Fourier in the chat. Okay, we're going to go back. Going back to the whiteboard. Okay. Again, type Fourier in the chat if you use Fourier transforms. Okay, so we're going to go back here. We're going to solve this integral. We're going to go to another page if it permits. Okay, I have to go to page, one of these pages here. Again, type Fourier in the chat if you use Fourier transforms. That's a problem for later. We'll look at that later if we have time. Can't guarantee we'll have time, but we'll see what happens. Okay, so we're going to look at going to this problem. Okay, so we're going to continue the problem. So we had the Fourier, that was a Fourier transform of curly f as a function of f as a function of x as a function of omega, and this was equal to the integral. Might make integrals a little better and more curly. Minus infinity to infinity of e to the whole negative power of a plus I plus I omega I omega by x in parentheses, omega by x parentheses with respect to x. Okay, so but we need to use U substitution, right? Why do we need to use U substitution to integrate? Simple. Let u equal to a plus I omega times x. Okay, so therefore my du, that's my du, my differential would have to be a plus I omega, okay, with respect to x. This is my differential. Now, what do I replace with dx? What do I replace with dx? Think carefully here when I do this. This is a constant, right? I have to divide by a plus I omega, so my dx now, right? So my dx is equal to du divided by a plus I omega. That is my dx. And I will now substitute in, okay? I will now substitute into our integral above. Okay, so now this is going to become, right, Fourier of f of x as a function of omega, and this is equal to integral from minus infinity to infinity of e to the u, e to the negative u, e to the negative u. And then after du, my du over a plus I omega. I want to replace all x's with u's, right? So this is going to become du divided by a plus I omega. Okay. And this should have been a negative. Let me think here. U, okay, so let's put over here. U was equal to negative in parentheses a plus I omega, so this should have been negative. That means this is negative. That means I have all this negative. Be careful here with my writing. Okay, so Fourier of f x is a function of omega. Okay, and this is equal to negative of this. And I can bring also the constant in front. So this is now equal to negative 1 all over a plus I omega, and then integrate from minus infinity to infinity of e to the negative u du. Okay, any questions? This is case 1 when absolute value of x is x, where x is greater or equal to 0. Okay, so this is what we have so far. And then integrating this is very simple. I mean, I can say this is negative 1 all over a plus I omega. So negative a plus I omega. Okay, I'm going to put a limit here soon. Not yet. What should I do? Anyone have ideas? What should I do with my integral? Well, first off, this is a improper integral from minus infinity to infinity. Okay. You got a weird exponential here. It looks a bit funny and off. Any ideas? Anyone coming in? This is S.T.E.M Online Academy. Office hours and only office hours. Pretty much taking up homework problem that we did from last live show. For anyone who's seen last live show, come in. And also for anyone new who has questions on Fourier transforms and Gaussian integration. Conceptual questions, anything algebraically getting you stuck. Okay, let's see. I'll continue to plow through this problem. Okay, let's go back. All right, so we have negative 1 over a plus I omega. Okay, and then we have this integral from minus infinity to infinity. Okay, what I'm going to do is I'm going to write it like this. I'm going to put parentheses here. And I'm going to say that since we have it from minus infinity to infinity, I can say this is from integral from minus infinity to 0, okay, of e to the negative u du, okay, plus, okay, plus integral, right, from 0 to infinity, okay, of e to the negative u du. If that, usually that makes things simpler, okay. And then from here, why did I write it like this, though? Like, why did I split up this integral and add them and then have different bounds for the limits of integration? Why did I do that? What was that going to give me anyways? Why did I split up the integral like that? Because there's an identity that states that if I take the integral from minus a to a, right, it would be from minus a to 0 plus the integral from 0 to a, right? That identity, that integral identity. Okay, so that's why I split it up like this. And then also I can rewrite it and say that this is negative 1 all over a plus I omega. Okay, and then this is all in parentheses. Okay, I'm going to put a limit here actually, because quite often when we're dealing with bounds to infinity, we want to say that it approaches infinity, plus or minus infinity, not equals plus or minus infinity. Okay, so let me put this over here. So I'm going to put square brackets, and then I'm going to say limit. So limit as t approaches, let's say, infinity, okay, of, let's put parentheses again, and we're going to integrate. Okay, we're going to integrate this, so it'll be integral from, let's say, negative t to 0, e to the negative u du, plus integral from 0 to t of e to negative u du. Okay, and then this is all going to be square brackets. Multiplied by a factor of negative 1 all over a plus I omega. That's the constant in front of the entire improper integral. I hope you guys are finding this interesting. Those of you, even if you don't know Fourier transforms and you want to hop into the channel because you like integrals, please come in. Integral or series fans, please come in. Ask any questions related to integrals. It will be handy if you're talking about asking questions on Fourier transforms and Gaussian integrals, because that's what this office hour is mainly for, right? It's office hours plus advanced problem day, okay? All right, so anyone know how to tackle this integral now? Yeah, it looks like a mess. Anyone have any idea how to do this? Again, these problems are meant to get your blood boiling and the fluids in your brain thinking. All right. As I wait for more people to come in, and maybe you just came in as well, take a dive at the Fourier transform. This is supposed to keep you preoccupied. At least you're doing something, right? So more people could come in, maybe ask some questions, or if you want to ask a question directly. Right, just to remind all of you, we're just looking at proving that e to the whole power of negative a absolute value of x is some Fourier transform, using the Fourier transform definition, minus infinity to infinity of e to the negative I omega x dx gives us some Fourier transform, right? This is a Fourier transform that I've highlighted in yellow. Okay, let's go to the next page. Again, just to let you guys know, Fridays will be office hours. Okay, so Fridays at 7 p.m. Eastern time is always office hours. Right, maybe next Friday will be a different section of my book, right, on advanced integral methods. Okay, so each Friday will be office hours, and the office hours are meant to ask questions that you had difficulty conceptually understanding, and or homework that we want to take up. Usually on Wednesdays, I'll assign a homework problem. Friday, we'll take it up. And the homework problem is related to a concept from my book, okay? All right, so let's go back here. As I said, I put this problem up as a homework problem. So let's see if we can complete it. So we have this integral, the e negative u. The u was from minus infinity to infinity. Split it up because it had the bounds from minus infinity to infinity. So you can write it as two separate integrals. But my question to you is how to complete it. How to complete this integral. Well, first off, we put a limit on our bound of infinity, right? Because I want to say that it approaches infinity, never it's equal to infinity. So put a limit as t approaches infinity. T is some dummy variable I invented. Okay, and then integral of e to the negative u, c negative u. Okay, so if you have to rewrite this, right, so this is going to be -1 all over a plus I omega, all in square brackets. I'm taking the limit as t approaches infinity. Okay, this part here becomes e to the negative u now. Okay, boundary from negative t to 0. T to 0, same over here. Plus this integral from 0 to t to negative u du. That's going to be e to the negative u. Boundary from 0 to t. 0 to t. Okay. All right. We know that e to the 0 is going to be 1. So that limit's going to be 1. 1 minus 0 will be 1. Okay, so 1 minus minus, let me see here what's happening. Yeah, so this would be equal to -1 all over a plus I omega, okay, I omega, all in square brackets, okay, all in square brackets. So we can rewrite this as the limit as t approaches infinity, okay. Put the limits of integration in for e negative u. This is the e to 0 is 1. So 1 minus e to the negative t, okay. And then we have plus parentheses, plus in parentheses, we have e to the negative t minus e to 0, e to 0, okay. Right, so these parentheses, 0 is 1. Okay, this over here should be what? Anyone see anything interesting happen? E and negative t is approaching 0. Okay, e and negative t has to approach 0. This is approaching 0 because as t approaches infinity, e to the negative infinity is 0. That goes away. Over here, e to the negative t. T is going to infinity again. Yeah, infinity. This goes to 0. Okay. All right. Any questions on that? That should be straightforward. By the way, this is going to be a negative. This is supposed to be -1. Okay, so this is actually a +1. Actually, this is a question I want to ask you guys. Even though it's small and not as important, why does it matter if it's plus or minus? How do we know that it's a plus here? Yeah, that's more important than all this other stuff that I wrote on the board. Why is the plus matter? The plus symbol. Because it's negative, negative. When we integrated, let's be careful here, right? We're going all the way back when we integrated e to the negative a plus I omega powered by x, okay? We let u equal to negative ai plus I omega. So du is going to be a differential with the negative, okay? So dx is a differential with negative du divided by a plus I omega, okay? And if that's the case, right, this should have been negative. Okay, so I should be careful how I'm writing this. Over here should be negative. Okay, think about that. It's not tricky. It's just sort of hard to see because I sort of split up the integral right away into its individual forms. I decompose it. Instead of having minus infinity to infinity, I put the zeros in for the upper and lower limits of the separate intervals. Okay. So that means that this is just equal to, remember, it's 1 plus 1, so 2. Okay, so this is going to be 2 all over a plus I omega. Okay, so then we get 2 all over a plus I omega. Very straightforward. Okay, let me make some more room here because otherwise we are getting in the way of our second question. Okay, let's move over here. Now we have a real number over a complex number. What do we do when we have a real number over a complex number? Algebraically, what are we supposed to do? So right now we've got 2 all over a plus I omega. What can I do with that? Come on, guys, what can I do? Simple, right? Get a complex conjugate, right? I should multiply top and bottom by a minus I omega, right? So multiply by a minus I omega, a minus I omega. Okay, so this is now 2 by a minus I omega divided by a plus I omega. Okay, in the denominator, so the complex number, a plus I omega times a minus I omega, right? This is now equivalent to saying 2 by a, so 2a minus I omega, 2a minus 2I omega divided by a squared minus I squared omega squared, difference of squares, right? One follow. Okay, and then from here, what I can say is I got 2a divided by a squared. I squared is 1, so this would be a squared plus omega squared. Okay, minus 2I omega over a squared plus omega. I split up into the real and the imaginary. Okay, the real and imaginary. Let me highlight. This is the real. Okay, this is the real as a function of omega in this case, and this is the imaginary part. Imaginary part as a function of omega, where omega is the omega space. Okay. Okay, from here. And we're only interested in the real part. Okay, we should only be interested in real. Okay, so what should it be? Remember, what were we trying to solve again? We're trying to show that f of x, which is equal to e to the negative a, that's the value of x, right? Implies we get a Fourier transform of 2 times 2 times a all over a squared plus omega squared. Okay, and over here it's just going to be 2a over a squared plus omega squared, okay? And we've proven it. Right? We don't need the imaginary part. We're only interested in the real part. The real part is what we're looking at. We can individually choose real or imaginary based on the thing of the question, okay? All right, so I think it makes sense. Sorry for those of you who didn't come in from last live session. I sort of solved the problem myself. Or for anyone new who wanted to see it, I couldn't wait forever. Right? It's a live show. It's an office hour. All right. All right, so we have that. Make sure I erase this here. Okay, let's make some space here because we have too much. We got too much math everywhere. Okay, so make sure I start erasing. Erase, 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 erase. Okay. Once again, put in the chat Fourier if you've seen or used or heard of a Fourier transform before, and you're interested in either learning more, getting up to date on your integration. Make sure anyone's coming in the chat. Make sure I erase this, because otherwise I don't like messy boards with overlapping equations and other problems. Okay, we're just looking at some problems here. In the meantime, mainly this is an office hour. You asked me conceptual questions from my book, Advanced Integration Techniques, where we're looking specifically at the section of Fourier transforms and Gaussian integration. Fourier transforms, Gaussian integration. Put Fourier in the chat if you know what a Fourier transform is, or if you use the Fourier transform. Please put Fourier in the chat. Let's make math great again. Come on, come on, come on. Make math great again. Who agrees? Put math in the chat if you want to make math great again. Okay. And don't be shy. Please write something in the chat. Right? Please don't be shy. We've got all right. So yes. So far what we've been talking about. Okay. So let me see here. Just to let you guys know what's on today's menu for new people who've came in. It's office hours. Okay. So we're going to be looking at continuing, or if you're new here but know Fourier transforms and Gaussian integration, we're going to see talk about those stuff. If you have any questions on those conceptually or computationally, anything that you forgot that you want to talk about, maybe for your classes, university classes, or for self-interest, please don't hesitate. This is the place to be. I know this stuff inside and out. And we're also going to discuss the structure of waves and stuff like that. Okay. So if you have any problems whatsoever on these topics, that would be great. Specifically, this office hour is tailored this Friday, like today, Fourier transforms and Gaussian integration. Okay, because that's what we did in our last live show. So we took up a problem. I sort of erased this, sorry. But taking up any homework problems from before that any students had trouble with, or any new people who want to come in and have conceptual problems on these topics. Okay, anyone have conceptual questions on this? Anything on Fourier? Again, type Fourier in the chat if you already know what a Fourier transform is or have used the Fourier transform. Okay, we've already shown the last. Unfortunately, I erased it. I erased the solution for this guy right here. But however, though, if you're new and you just came in, take a try at proving that this is the case. That if f of x equals e to the negative a absolute value of x, its Fourier transform is 2a divided by a squared plus omega squared. And please, if you're doing it and you've found a solution, tell me how you did it. Part of the proof is on the board. The absolute value function, e to the absolute value function. Again, type something in the chat if you're new. Let me know that you're here. Okay, so yes, we're talking about Fourier transforms. All right, and what we're going to look at, so as I said, I took up a homework question. That's already out of the question. And ask any other questions that you have based on the same topic. Let's do a Fourier transform warm-up. Okay, let's look at this guy solving this integral right here. Who wants to take a warm-up for anyone new? Anyone want to solve this integral? It's right here. Everyone take a wing at it. It is office hours. You have any issues on how to start? Just ask me questions, what it is. If you know how to integrate, this should be pretty straightforward. Anyone at all? Okay. You should notice something here. All this is doing the following. Okay, so the solution, right? Solution SOLN. Okay, let's rewrite it as the following. So this integral from minus infinity to infinity. Again, it is a Fourier transform because it has this factor, e to the negative I omega x dx, and it's integrated from minus infinity to infinity. This can be written as e to the negative x minus x naught, all in parentheses squared, minus I omega x dx. Why did I write it like this? How did I write it like this? Why did I write this integral like this? Very simple. Same bases. Right? E. When you have two bases that are same, multiplied together, you add their exponents, I left it like this. Then from here, what I'm going to do is I'm going to expand out maybe this portion here. Okay. I'm going to do that. It's going to be handy. Okay, so this is going to be equal to integral from minus infinity to infinity of e all to the power of negative x squared minus 2x by x0 plus x0 squared, okay, minus I omega x dx. Any disagreements? Anything that you'd like me to explain? Anything at all, let me know. Please let me know if there is an issue you conceptually are not understanding. Again, this is office hours. And even this integral here is just to get your juices flowing. If you just got the start of this lecture and you just came in, again, it's a Fourier transform. Oh, guys, communicate in the chat. Well, I want you guys to go back and forth with me. Tell me what you understand, don't understand. Tell me anything. Anything at all. Anyone have any questions? Okay. Okay, at the moment, there aren't questions on this. I think this is pretty straightforward. Okay, now you'll notice that this is a bit nasty. There's the x minus x naught squared, the minus I omega x. Okay, so you can see we have a bit of a mess. I've expanded out the perfect square trinomial in the exponent. Okay, so what should I do from this point on? Try to factor in, well, factor in, multiply the negative inside. Okay, why would I want to multiply that in? Why should I multiply the negative one in here and distribute? Should I do that or should I do something else? This looks a little bit deceiving because part of it already is in some form of perfect square, the x minus x naught all squared. Was it necessary to expand out the trinomial or no? Like, is it necessary to do this? Come on, guys. I want you guys to don't be mute. Well, if you had it like that from the previous step, let me highlight this. This integral right here, okay? You know, you leave it the way it is. Let's say the x minus x naught squared minus I omega x, okay? And let's say, well, I need to know what my b is. So I want to complete the square. However, though, do I need a b? Or is it already in completed the square? Is it already a perfect square trinomial? No, we need to expand out collect like terms, right? Put the negative inside and then collect like terms. Watch what I mean here, right? So this is going to be integral from minus infinity to infinity of e to the negative x squared. We'll put it over here, negative x squared plus 2x0 minus x0 squared. Okay, so this is what we've got right now, minus the I omega x power dx. Okay, then what I'm going to do is I'm going to write in the form ax squared plus bx plus c by collecting like terms. Okay, so integrate from minus infinity to infinity. Okay, so what you're going to get now is you're going to get, so collect all like terms. Okay, so what I might do is I'm going to say e to the negative power of, let's see here, x squared minus x0 squared plus x by 2x0 minus I omega dx. This part is correct. This part here, I'm actually thinking that might be problematic. Anyone can help me with this. We may have a bit of a problem. If you notice, this integral here is a little tricky. That's right. Integration can be complicated, and this proves it. So you may need a refresher. That's why a lot of you should come in. Even me, I'm having a little trouble here. X squared minus x naught squared. Was it necessary to expand out the perfect square into a trinomial? Oh, it wasn't. Let me see here. Couldn't have done anything. Like if I needed u substitution right away on the x minus x naught squared, like u equal to x minus x naught squared minus I omega x and b minus I omega 2 by x minus x naught. Then we make du 2 by x minus x naught minus I omega. Oh, we got a bit of a problem here. The x squared minus x naught squared. That's interesting. Seems like we've reached an impasse where we're getting into a circular issue because the x minus x naught squared, that trinomial there is a bit problematic. You don't know what to do? Anybody? Well, right here, actually, let me see. X squared minus x naught squared. X squared is a number. Yeah, we can. This x squared is a variable. X naught squared is a constant. Yeah, we can rewrite it like this. No, so this is not exactly it. No. Yeah, I see it now. It's going to be negative x, because the x naught is a bit annoying, minus x squared plus, let's say 2x. Oh, no, sorry. Plus parenthesis 2x0 minus I omega by x. And then minus x naught squared. Okay, all in the parentheses with respect to x. Now, the reason why I did that is because the x naught squared is a constant. Okay, so now this is written. If this is a function of x, this is a standard form of quadratic equation in our exponent. So this is now written in the form a x squared so that plus bx plus c. Right? A is negative 1, b is this portion here, c is purely a constant. So anything that is not an x is a constant. So this works, right? This is the x squared. This is my x squared. This is satisfied. This is my x. In front here is my b. And this is my c. And the negative 1 is the a, you can say. Okay. Any questions on what I just did? Everybody's shy today, even though I notice there's like a few people here. Don't be shy, just type something in the chat. Okay, so now that we got that, what we're going to do is we're going to be able to what's it called? Because it's in standard form, is to complete the square on it. So what's my b over 2? Well, we know what b over 2 is. So let b over 2 all squared. B is 2x naught minus I omega. 2x naught minus I omega all over 2 all squared. And that means that we get 2x naught minus I omega all to the power of 2 divided by 4. Okay, it has to be like that because the top part is just two different variables. So it's going to be a perfect square trinomial, even though they're constants, and divided by 4. Okay, and then plug into the integral. So this is integral from minus infinity to infinity, okay, of e to the negative x squared. Okay, e to the negative x squared plus, let me see here, did I have anything? Oh, mistake. There's a negative in front of my constant. Ah, damn. Before doing the b over 2 squared, I just noticed something. Because you want the right b value. Okay, anytime there's a negative in front of your x squared, you need to be careful. This is what makes completing the square hard for a lot of people. Okay, you want to make sure that you factor out the negative first in front of the entire quadratic equation. So do it again. So it's going to be integral from minus infinity to infinity, e to the whole power of negative, parentheses, x squared minus, parentheses, 2x 0 minus I omega by x. All right, so like this. Okay, and then minus, plus x0 squared, because the negative times positive negative. Parentheses dx. Now from here, let b over 2 all squared, b over 2 all squared be 2x naught minus I omega, where x naught and I omega are constants, divided by 2 all squared. This means I get 2x naught minus I omega squared divided by 4. We don't need to expand out the trinomial. Everyone following so far? Following the what's going on? Let me know if you need any assistance. Again, this is supposed to be tailored towards conceptualization of Fourier transforms and Gaussian integrals. This is office hours. If you need help on this, please drop in. Okay, and then from here, let's continue. This would be integral from minus infinity to infinity of e to negative parentheses x squared minus parentheses 2x naught minus I omega by x plus x naught squared plus, let me highlight what I'm putting in, my b over 2 all squared plus or minus it, 2x naught minus I omega all squared divided by 4. Okay, and then minus 2x naught minus I omega all squared all divided by 4 in parentheses. Multiply the negative in to one of these values. I get to choose which one. I'll do positive 2x naught minus I omega all squared divided by 4. So this becomes minus 2x naught. And the next line, I can't write it here yet. Let me just put a dx. Okay, I'm going to keep writing. So now I got this equal to integral, right? Integral from minus infinity to infinity, e to the negative x squared minus 2x naught minus I omega by x plus x naught squared minus parentheses 2x naught minus I omega all to the power of 2 divided by 4. This is going to be minus on the outside, minus 2 by x naught minus I omega all divided by 4 all to the power of 2 dx. Okay. Any questions so far? Remember, this is office hours. Anyone coming in who either wants to tackle a very hard Fourier transform or needs help on understanding the basics of Fourier transformations and Gaussian integration, this is office hours. You're free to ask me anything on those topics. Okay. S.T.E.M Online Academy, where we bring mathematics and physics together, showing the applications of mathematics to help strengthen both critical thinking and visual spatial skill, which in turn will help your mathematical intuition. Okay, let's get back to it. Okay, so we're looking at this integral. Okay, so now we have all of this. This gets a bit, we have a serious monster on our hands. Don't worry, as long as it's in the form a squared plus b squared, a plus b all squared as a perfect square trinomial, this is easy. So taking this integral here, minus infinity to infinity, this can be compressed as e to the negative. Notice what a is here. This is my a. Okay, let me tell you what. So we have ax squared plus bx plus c, right? And we want to make it go to a plus b all squared. So what do you think it is? Well, it's going to be x, e to the negative whole power of x, minus, all in parentheses, 2x naught minus I omega, all divided by 2, all to the power of 2. So when you expand this, okay, you should get, let me see here, is there an x? Sort of put an x here. Yeah. Oh no, there's no x, because when you do the perfect square trinomial, a squared plus 2ab plus b squared, it comes out. Yeah, x minus b squared. Let me be careful here. Probably forgetting my x naught. Anyone new coming in? Not yet. Yeah, I hope anyone who's here is already enjoying what's going on. Okay. But please participate. Ask questions. Please ask questions. How are we going to do this? By the way, when we expand this out, so far we're getting this part, which is correct. However, and we get this. Let me see here. Should be getting this as well. Unfortunately, though, we don't get that x naught squared, which is a problem. Anyone know how to deal with the x naughts? How do we put the x naught in such that it is written, it stays, it preserves the same form when completing the square? Well, the first part is right. The last two parts are a little bit tricky. By the way, this would be plus. This would be minus. This would be plus. This is a plus. And that should have been a plus. I got it the wrong way around. I should have done it like this. Otherwise, I don't get that trinomial at the end. X plus. Let me see here. Oh yeah, that's interesting, because now we have x minus 2x naught minus I omega all over 2. We have a bit of a problem. anyone know how to deal with this? Right, we got 2x naught minus I omega. So look, right here, we've expanded out x squared minus 2x naught minus I omega all x times x, and then we have the x naught squared that we have to deal with. So the first two parts are okay. That's why I highlighted in yellow. The last part, 2x naught minus I omega all over 4. Yeah, that's fine with 2x naught minus I omega all over 2. Also, when you square the whole thing, you get that expression. I think this is entirely correct. Negative. Oops. Negative. If I had put a plus and that wasn't negative, let's say you had a plus there. Yeah, I put a plus. Put a plus there. Oh, right. Make this negative. Yeah. Negative is positive. Wait, no, we don't need that. And then we still have this on the outside. This is simplified to x naught minus I omega all to the power of 2 divided by 4 dx, right? Okay, this is what we have. Inside here is where we have an issue. Anyone want to take a guess? Anyone want to take a guess at this nasty thing? Remember that x naught omega or constants x is what's changing. Okay, so any ideas? Any ideas at all? Okay, so here, right, this is taken care of. This is, remember, this is a squared minus the 2ab. This part over here, this would be like our plus b squared. B squared. We should have over here, like put in brackets, minus x naught. So that's when I do it like this. In other words, this would be my a. This would be my b. This is in the form of a minus b all squared. It's going to be that. I do that. Plus the x naught squared. I think we've got it here. Yeah, because negative is positive. X naught squared over there. Yeah. X by x naught, x by x naught, x by x naught, x by x naught. x by x naught. X naught divided by x. X naught divided by x squared. So it should be something like this, I believe. I may need correcting on this. If someone can notice it, either during the live show or after. Let me know if there was a mistake in my completing the square here. This is a really nasty one. Okay. And then over here we get integral from minus infinity to infinity of e to the negative x. Okay. Negative x minus parentheses 2x naught minus I omega in parentheses divided by 2 minus x naught divided by x, all to the power all to the power of 2. And then times e to the power of 2 x naught minus I omega, right? I omega all to the power of 2 divided by 4 with respect to x. Oh, yes. Glad you are back. Nice to see you again. Zylig. I'm sorry. Yes. It's good to see you again. There is still 20 minutes left. Okay, I hope that's okay. All right, so we're looking at something interesting today. All right, you have any questions that you'd like to ask? This is office hours today. So we're going to be talking on the topic of integration. Anything from the last live show that you have, any misconceptions or anything you want to go through. Oh, I appreciate it. Yeah, that's a good thing. Thank you so much. Are you? I forget. Are you a high school student or are you university? High school, university? Let me know. Oh yeah, you're the 10th grade guy. Yes. All right. Well, I hope this. I hope last time when I was explaining about how integration is a way to calculate the area under a curve, how it's really handy. Okay, it's really neat stuff. Right? You should read up on it if you have time, and also you can attend my lectures here on YouTube. Right, so they're always fun and interesting. All right, perfect, Silent. All right, don't mind me. I'm going to go back to the whiteboard. Okay, and just talk about some stuff here. You may be able to relate to this. Okay, if you've done completed the square before. Okay, this is a nasty completing the square. As you can see, I was looking at an integral where we had to complete the square on this guy because you can see that this is some form of ax squared plus bx plus c in the exponent, ax squared plus bx plus c, if you know what I mean. Oh, perfect. Yes. Thank you. So I'm sure you can relate to it. It's a standard form of a quadratic equation. All right. Let me know if you know what I mean by that. See you can sort of relate to that. The only thing here is it's nasty. I have to complete the square on all of this. And I reduced it down all the way to this down here, unfortunately. Yeah, this was nasty. Yeah, this was my completing the square. In other words, I put it in the form of a minus b all squared, if you can relate to that, right? Because completing the square goes from a squared minus 2ab plus b squared to a minus b all squared, right? Let me know with a nod or anything. Ah, yes, yes. So I seem to be understanding. Good. Okay, so I'm going to continue on here. So since it's the form of that, right? For anybody else, you'll probably notice what comes up here, right? Okay, you'll notice that I can move this to the front. I can move this part here to the front of my integral. Okay, and the reason why I can do that is because it's a constant. Like omega I and x naught are not x, right? When you integrate anything, you guys have noticed, right? When you integrate anything, only the variables that you're integrating with respect to are within the integral, right? So this is going to be over 4 times integral from, just 1 second, integral from minus infinity to infinity of e to the negative parenthesis of negative x minus double parenthesis, and the parenthesis again, 2x minus I omega divided by 2 minus x naught divided by x, parentheses again, close parentheses, because it's in the form of a minus b all squared dx. Okay. Thank you, Zylik. I appreciate that. Let's see. Okay, so we got all of this. All right, so we got all of this right now. Now it looks nasty. How on earth are we supposed to integrate that? Even normal integration methods don't work. I did talk about something to do with Gaussian integration before, and not only in the last live session, but even in previous live sessions. So anybody else who's familiar with integration should know what I mean. How can I integrate that? Anybody in the live chat right now who knows how to integrate this? Sorry, I need some water. Anybody know? Chain method. Oh, now Zylik. Oh, you remember from last time? I was talking about chain method. Were you the one that asked me about chain method last time? Zylik, just want to clarify. You asked me about the chain method, or was it somebody else? I don't think it was. I don't think it was. Was it you or was it some other guy? Was asking about chain method. There's no chain method here, by the way. No chain method. Yeah, exactly. Yeah. Okay. No. And the reason why, let me explain. Okay. You only take the chain method of an integral if it's written like this. If your integral is written as some form like this, integral of u dv equals uv minus integral of v du. This is not replicated here. It's not in that form, as you can see. Okay. So no. This is not. No chain method under these conditions. Okay. That's the mathematical form, if that makes sense. Okay. And you understand what I mean, at least, because you know that quite often in math, it needs to be written in a certain mathematical form in order to use it. Okay, so now we've got this. All righty. Okay. Now, the way to do this is using Gaussian integration. Okay. Notice, I'm going to highlight this. Okay, that the integral from minus infinity to infinity of e to the negative u squared, doesn't matter what I call it, with respect to u, is equal to root pi. There's another formula to integrate anything that's raised to the exponent 2 that has a base e. So base e raised to the exponent 2 is always equal to root pi, regardless of what I call it u here. Okay. So what that means is if I were to do that, let me see here. I think I'll leave that for homework. Yeah, that's going to be a homework question for anyone who wants to try it. Okay? Because I know how to do it. I want you guys to have a headache. or if you like to have a massive challenge, do it for homework. Okay? But this one's nasty. Alrighty? All right, so anything for homework? Anyone want to try this for homework? Oh, I appreciate it. Yes, go ahead and give it a try. Even though you're grade 10, I don't know if this is appropriate, but yes, go ahead and give it. I still believe in you. Yes. So 1 second, let me make sure that anyone else is coming in. If not, I might get going. Let me see here. I wanted to mention that. Okay. So I think this will be yeah. Just give me a moment. I'm going to think about how I'm going to. I think this will be, unless there's any last minute questions. You're welcome, Zylik. I'll always come back to come in. I'm available Wednesdays, Fridays, and Sundays. Yeah, Wednesday, Fridays, Sundays. Okay, just let you know. All right, have a good one. I'll see you next time. All right, guys. That's it for tonight's office hours. I think we'll stop here. Okay. So if tonight's sessions opened your eyes to the structure of our Fourier transforms and Gaussians, and also waves, quantum waves, everything we just did is a taste of the mathematical depth that's inside of my book, Advanced Integration Techniques. The book contains Fourier methods, complex analysis, Gaussian integrals, special functions, open-ended research level problems, and real intuition for advanced calculus. Okay. So if you truly want to learn applied mathematics the way researchers learn it, this is the right book for you. Okay. You can get the book in the description below the end of this YouTube video. And yes, it will be in the description. Have a good night, guys. And I'll see you guys on Sunday. Sundays is when I also have, we're going to go back to a regular live session. And it will be on another topic of my book. Okay. All right. Oh, when do I stream? You're asking, Zylik. Yeah, Sundays at 12 p.m. Eastern time. I assume you're in a different time zone, so look Eastern time and convert it from your time. Does that make sense? Okay, good. Yeah, 10 p. Sorry, it's 11. Sorry, 12 p.m. 12 p.m. Sunday Eastern time. Got it. Perfect. All right. Have a good night out, and I'll see you guys next time. Bye for now.